Okay. First of all, this event is like the first time that we conduct under the name of International Day of Light. We usually arrange this event as Photonics Day for the past few years. Actually, we try to organize it every year, but unfortunately, because of the pandemic, we missed last year. But this year, finally, we could have a chance to conduct it online. Thank you for all joining us today to celebrate the International Day of Light. Who are we? We are OSA-SPIE METU student chapter. And also we are trying to be Optics Photonics Society in METU. We represent these two of the most prestigious optical societies among the world. Both are well established and leading societies in their fields. OSA, renamed as the Optical Society, was founded 1916 in order to assemble scientists under the roof of under one roof to lead research and educations. And SPIE is similarly was founded 1955 to create a specialization in optical instrumentation. And we are their representatives since 2011 and 2013. And our aim is to bring students and staff interested in optics and photonics fields together. And so here we are conducting these events and seminars with our professors from both our university and other universities. And again, welcome to the celebration of International Day of Light with us. We are too happy to see you with us. Thank you for listening to me. And by the way, my name is Cemre and I'm the president of the society.
Well, thank you, Cemre. Before we start our event, I would like to firstly show you the program of the event. We will start by a small talk and some celebration of the International Day of Light, and then we will have small talks with on light with Dr. Alpan, and then we will have Dr. Fırat Es. He is from KalyonPV, and he will give us a seminar about photovoltaic cells and solar cells. And then we will have Dr. Alkan Gülses. Actually, the reason why we made the event in the evening is to be able to squeeze a bit the time zone difference. It's like 10 hours from his, I guess now in Texas. And he will join us, giving us a seminar about laser shaping and hologram. So welcome again. I would like to start the celebration with a small video, remind us about the campus. It's now empty. So let me share it and let's go to the campus and the physics department together. And then come back.
The International Day of Light is celebrated on 16th of May each year, the anniversary of first successful operation of the laser in 1960 by physicist and engineer Theodore Maiman. This day is a call to strengthen scientific cooperation and harness its potential to foster peace and sustainable development. The International Day of Light is a global initiative that provides an annual focal point for the continued appreciation of light and the role it plays in science, culture, and art education, and sustainable development, and in fields as diverse as medicine, communications, and energy. The broad theme of light will allow many different sectors of society worldwide to participate in activities that demonstrates how science, technology, art, and culture can help achieve the goals of UNESCO, education, equality, and peace. Each year, we are, as OSA-SPIE student chapter, celebrating the International Day of Light under the name Photonics Day at Middle East Technical University. Unfortunately, last year, due to the current circumstances of the pandemic, we are now more than a year far away from our campus, trying to remotely handle our courses and at the same time trying to care about our health and the health of people close to us. Hopefully, this situation finds an end soon so we can gather again and discuss more about our passion toward the studies of light.
We will have Zainab, she's a PhD student, and she would like to give us a talk about a brief history of optical and light science.
I am Zainab Karsagi, a physics PhD student, and as you know, today we are here for celebrate the light, not just for the scientific, but also art in the art, also cultural environment, what the light contribute our lives. So let there be a light, I say, and maybe you know, maybe you don't know why the 16th of the May we are come here. This is a very important day of the humanity because really rare in the science history, it is seen that some application is emerged and its results actually change whole the lives and whole the history. And one of them is the laser actually. And this is 16th of the May, the first operation of the Ruby laser day. Actually, the Theodore Maiman operate the laser after the maser is found. He think that if the maser, I mean the microwave stimulated emission is found, therefore he can say that laser also can be operated, and of course the laser theoretically also can be taught. And Theodore Maiman operate with the Ruby a laser, and he succeeded, and he just sent his paper, write a very short paper as you see here, and write this, sent this paper physical review, and then the editors surprisingly reject the paper because they think that the laser is not a topic that's so important. The optics is actually considered that as finished, fully finished. There is no open road to go in the optic, they say. And then he think that to send a paper, another important journal, Nature, and then they receive it. Actually, the first rejected papers date is the 16th of the May. So we just celebrate is the rejected day actually, but the Nature accepted in the August in the same year. And whatever it is, the 16th of May is accepted for the very important day of the human in scientific, in cultural, in art, in any aspect of the life to enlighten the human life. So laser is actually open some roads for the humans. How? First of all, it's provide a communication in the worldwide. Large amounts of communication is not possible without considering the fiber optics. And after the fiber optics communication is achieved, so and the internet is and the faster communication is succeeded in the world. So as we can see that unlike the history, people can relate each other and the scientific environment faster and faster communicate in each other, and the scientific papers and scientific improvements are increased. Also, the communication also increased some of the cultural things in the world. Also, there are another aspect, this CD, DVD, and also digital photography, holography, and many other things with the laser invention can be possible in our life. So it is very important thing to have a controlling the light, because you think about that light is just a sense of the life, actually. When they think about the plants, they just create chlorophyll and oxygen for us, for the nature, because of the light, just because of the light. So when there's a light and you can control the light, actually life is easier for all of us, and the controlling of the life is possible. So not only for us, maybe light is important, for all the human and history, light is a very interesting subject. They think that some kind of light is considered by them some kind of goddess or some kind of holy thing in the ancient times. For example, Egyptians think the sun and the lights coming from the sun just eyes of their god Ra, and the ancient Greek think the vision as possible only with the Aphrodite leads a light in our eyes, and then we can see things. Before the going further, I can say that of course there can be many way to explain the history, but it is commonly used way to make 4 stages for the improvement of the light. This is one of them is the ancient times. Not only Greek, I think, also in the Eastern society have something about the light, but the ancient Greeks more make it scientific and more record everything. So we can relate more than the ancient Greeks. So also after the Greeks, there is an era of the Islamic era. Most important thing, most important person, Al-Hasan, actually Al-Hasan, Al-Haytham, or in the Western society it is called Al-Hasan. He is considered as a father of optics until his, actually only the vision is considered, not the light itself is considered, and not so many improvement is achieved up to Ibn al-Haytham, but Ibn al-Haytham make very important contribution. And as you know that the pioneer of the optics in the modern times is Newton and Huygens and Young with the double slit experiment, and Einstein, and of course the electromagnetic theory, Maxwell. They are called the European era. After the Islamic times, the European era, they in tremendous contribution to the science. And then after that, we can say that in these global times, modern times, after the laser is found, and then everything is not just geographically or timely, we just consider everything is more global terms. And as I said, in Eastern part of the world interested in light, also in the India, there are 6 ancient school. The most popular one is the yoga. As yoga, yoga, the Vaiheshka, see, this is the Vaiheshka, also important school of the India. And then in this school, they believe that everything in the world is atomistic. And then these atoms made up of, earth, air, water, and fire. And these four fundamental things and their atoms creates everything. They believe this in the atomistic view. And then light, they in their consideration, believed is the atom of the fire. And then they believe that in the atom, the atoms ray in the ray of light, atoms of fire in the ray of light, and their arrangement and their speed, actually their arrangement generates their speed and the characteristic of the light. It's interesting because it's very close to our understanding, also in the Newton's times, our understanding. And there's this light consideration is the first in the Eastern world, the physics of the Vaisheshka, it's the first introduction of the physics. But in the Greeks, they generally consider the vision, not the light itself. And they, as you can see in this illustration, they interestingly believe that the inside of the humanoid, as I said before, like goddess or some other thing, generates some light, and because of that light in the eye, we can see something. And as I said, interestingly, people believe that in many years that is true. Many big great brains like Plato, like Aristotle, Socrates, and this theory is accepted by all the Greeks. And after the Greeks, actually, there's the era of the Islamic part and then Islamic era. And this era, people just follow the ancient Greeks thoughts, and they first of all try to follow and understand their consideration. But Ibn al-Haytham and Ibn Sina argue against this idea, and Ibn al-Haytham make an experiment in the dark room, and he proved that it cannot be a light, the vision cannot be provided by the light within the eye, but the light coming from the object. And theoretically, Ibn Sina also says something about this before the Al-Hazan. He said that if it is possible, then how we can see in the darkness, for example. And then, as I said, that Al-Hazan, very important person in the optic aspect. And in his book, generally the last researchers found and credit for many things, but we know before credited by other people, like, for example, Snellius law and other many things, we credited someone else's. Modern researchers tend to give credit Ibn al-Haytham. So after the Islamic era, the Mongol destroyed every Islamic geography, and then their culture and their Iskandariya library, everything is destroyed, and just some of the Greek tradition and some of the Islamic Muslim scholars are in the Spain, carry this valuable information to Europeans, and these Europeans take them and make revolutionary thoughts on this, and they open a new era. For example, when we say the Europe in the light, the first one maybe come to our minds, the Descartes, and he follows the atomic point of view as like an ancient times people, and but his theory of light, therefore, is very considered by the atomic consideration. He just think that vision is something like that when the object is radiates something as a sound wave, and it is just propagates in the medium, in ether, and then coming to our eyes. He just think how the vision is proceeds. But the time is goes on. Ether still thinking, still stay in the consideration. But it doesn't matter where's the ether exist or not for the lights proceeding at first time until the Einstein proved it is meaningless to debate about that. And then Newton proposed a light, white light, has a component of the other colors, and then if the white lights passing through through a prism, it's divided into its components according to their mass, their speed. Therefore, red light, for example, according to its mass, is just a band more, unlike blue ones. And then it's very interesting thought of the Newton that he just considered the light as a particle, as we say, corpuscular theory, it is known. But also he invents some telescope. So also he knows that I think you know, not everybody think that, but I think that he also knows the wave nature of the light. He against some of the because some of the things like bending around a corner and some kind of things, but I think he just believed that also light has a wave nature or has an intuition about it. But you know, the Newton's has a very strange character and likes the power, I think so. I'm sorry. Okay. Actually, there are some things, but I make it faster. So the Huygens also, at the same time, think that light is not a corpuscular, but has a wave nature. And it is the very important and the greatest debate in this history of science. And by the Young double slit experiment, it is proved that light has a wave nature. And then Huygens has, you know, gained 1 point in this debate until the Einstein. Before going to Einstein, we understand the quantum nature about the radiation by Planck's contribution. Planck's actually interested in thermodynamics when he's a student, and he just observed that when the light absorb all the light, black body absorbs all the light but radiate only some specific frequency, radiated at this frequency. So he just think that there's some discrete frequencies that should be in the light radiation. After this major foundation, Einstein also think about it, the problems. First of all, until the Einstein, as I said before, there's a concept of ether and everything that the light propagate in the medium of ether. And Michelson Morley tried to find detect ether. They made an experiment, and this experiment shows that negative result, you know, the null result. There's no, they cannot detect anything. But the Einstein think that, okay, it is possible because the there may be no ether, but if it is there, if there is, doesn't matter. Just the light speed is constant because he postulated, and also he said that reference also the physics doesn't change in the different reference frame. So he established his special relativity with the constraint of the speed of light. And after a couple of months, he also established a second paper. And this paper, he just established a relation between energy and the mass. You know, the very famous formula E equals mc squared. And this is also benefit from the speed of light. Some important development is also achieved after the Einstein and the photoelectric effect, also Einstein contribution. The photoelectric effect, it shows us also light have a particle nature because the light comes to a metal plate and then an electrons just goes up, and then so it's like a billiard ball. There's a particle nature in the light, so it's used in the sun power when the light, therefore light sun light can be used to generate electric power. And these are the pioneers of the generating solar cells, these gentlemen. And thank you listening to me. And many important things with the light, I think, in our lives is made it possible. So I just, you know, make it shorter because there are so many things we can talk about. But thank you listening to me, and happy the International Day of Light to everybody.
Thank you, Zeynep.
Fırat Es is going to give a talk to us. First, I want to introduce him. He studied in physics department at METU. He did his master's and doctoral degree in METU, and he worked in TÜBİTAK Uzay, and also he worked in UNAM photovoltaic for 10 years. Now he's in KalyonPV. He is doing research and development manager right now. That's all.
Thank you, Elif. I will share my screen, right? Nanotechnology in PV applications, which is mainly my also PhD thesis, which I finished at 2018 in Middle East Technical University. But first, I will also give you some information about KalyonPV or factory and what we are doing. Because what we are doing is a very good example of light-matter interaction. We are using the energy of photons and given to the grid. So now we can use it in our homes or other places. Therefore, it is related. And also maybe some part of photonics, because my PhD was on texturing of crystalline silicon with nanostructures, where we were having some from geometric optics to going into some physical optics parts, because we were having very small nanometer range of structures on the surface of the silicon. and I will share the results and the industrial applications that where these two meet. So it's a meeting point of maybe photonics, photovoltaics, and industry. So this can be interesting for you. So let me start first with our factory. I will go fast, but please make any notes and ask any questions whenever you want after the presentation. I think we will do like this. So our project is mainly called Akka Karapanar project, which is Akka means Akka is renewable energy resource area, which means that government asks the companies to produce solar modules, photovoltaic modules, to be used, and they must be manufactured in Turkey, starting from the raw material polysilicon. So this project starts with a mainly made in Turkey solar modules target. So our factory is mainly opened in this motivation. So in Konya Karapanar, there is a desert which is 20 million meters squares. It is the only desert area of Turkey, and since you cannot do anything about agriculture there, it's best to use harvest solar energy there. So the main idea is to put solar modules in this 20 million meter squares of deserted area, and it will have a capacity of 1,000 megawatts installed power, 1 gigawatts installed power. And to make this 1,000 megawatts, we are going to produce 3.3 millions of solar modules there, and these modules will generate 2.6 to 2,600 gigawatt hour energy per year, and this is going to be about 20% of Turkey's solar energy manufacturing. So 1/5 of Turkey's solar energy manufacturing will be coming from this deserted area. And in our solar power plant, we will be using double-sided and sun tracking systems, so that the modules are tracking sun to harvest more energy, and they can get sunlight from the rear side of the solar cells also. So this is the photo. I will show more photos from Karapanar, or solar power station. It is the 6th largest solar power plant in Konya, Karapanar, Turkey. As I said, it's going to be having 3.3 million modules, which will be produced in 3 years in our factory. It's going to supply 2 million domestic electricity requirement. 2 million people will be energized with this project. And we are having 1,500 meters squared of SCADA center, where we are controlling this huge area, and we are having 5,500 meters squared R&D test area to test different technologies together with the power plant. So you can see the size of the power plant. It's a huge area. By car from one part to other, it takes around half an hour, 45 minutes. It's a very big area, and this part is completed part. There are lots of solar modules that are mounted, and when it's finished, this whole area will be covered with solar modules, and this is a top view. The project will continue around 3 years, and in 3 years it will be completely finished and energizing 1.1 gigawatts of power into the grid. And these are the unfinished parts are looking like this. You are putting modules here one by one, and this is a bigger picture. And this is the R&D area where we are using different installations. For example, you can see one of them is tracker. It's facing east and west, while non-tracked ones are on south and north orientation. So we are testing different technologies like crystalline silicon, different crystalline silicon solar modules, and maybe thin film modules and perovskite modules in the future. All these will be tested in the same conditions as the solar power plant. And to make the modules in this power plant, 3.3 million modules in this power plant, we established our factory in Ankara, Polatlı, Temelli, Başkent Organize Sanayi. It's a 100,000 meters squares of closed area under same roof. We are having 500 megawatts of manufacturing capacity, and now we are extending our capacity to another 500 megawatts. So, and at the end of 2021, we will be having 1 gigawatts of capacity, and it's integrated manufacturing, which means mainly in Turkey, most of the production facilities are producing modules, purchasing cells from China and connecting them to make modules. But in our factory, we are doing the semiconductor ingot, wafer, cell, module under the same roof. We are reaching 75% domestic production, and we have 1.4 thousand staffs working with 3 shifts every day, 7/24 hours. And we have a 2,500 meters squares of R&D center, which we are still establishing right now. Production started in August 2020. As I said, we are producing ingots, wafers, cells, modules. This is a photo from our first ingots grown. You can see a Czochralski grown semiconductor crystalline silicon ingot. It's around 5 meters length, and this is one of these photos. As I said, we are growing Czochralski monocrystalline boron-doped P-type ingots around 4 meters. And then in our first factory, in the wafer factory, we are using diamond wire cutting to cut these into semiconductor wafers, square wafers for photovoltaics, 156.75 millimeter full square and 180 microns, around 1/5 of a millimeter. And in our cell factory, we are taking these wafers and making semiconductor diodes, and we are producing solar cells so that they can have this photovoltaic effect to convert electricity. We are having 22.2% efficiency right now. We have bifacial technology. We are using monoperk structure and 70% of bifacial factor. And in our module factory, we are using glass frameless modules with double-side modules, bifacial modules. We have around 400 watts power per module, and again 70% bifacial, more than 70% bifaciality. And in R&D center, in our R&D center, we are working. We are having a 2.5 thousand meters square of area. We are having masters, PhDs, bachelors, and technicians. And since the 1st of September, we are an R&D center established by Minister of Industry, and we are working on new technologies and to get new projects together with different universities and different companies from Turkey and abroad to enhance our solar cell efficiency and module efficiency. We are doing some projects, as I said. We have around 5 external funded projects. One is being approved right now. 25 current projects are running, 7 projects are in preparation, and 4 completed projects we have in our R&D center. And we are mainly focused on new technologies like IBC solar cells, N-type solar cells, and perovskites, and localization and supplier development to increase the localization ratio of our solar modules. Recycling and zero waste, because this is a big factory using lots of chemicals. We are trying to be environmentally friendly and also increase the profit. So we are working also on recycling and zero waste and optimization development for the increasing the efficiency and decreasing the cost of our modules in our factory. And we are having some patents, applications, and other kind of stuff, which I will pass quickly. And we are, as I said, collaborating with different universities and from world and from Turkey, and we are trying to increase this collaboration. So mainly in KalyonPV, we are starting from polysilicon to make semiconductor ingots, wafer cells, modules, and we are establishing a strong R&D team to develop these technologies and to have better efficiency from our products mainly. And now I finished what we are doing in KalyonPV. Now I'm going to talk about nanotechnology in PV applications, which as I said, was a part of my PhD thesis. As you know, structure of a basic solar cell, you can say we are having a wafer. This is the cross section of a wafer, P-type crystalline silicon, and you can have an PN junction on this wafer where you have an electric field from N-type to P-type. And in the surface, you are having texturing for light trapping, which is the subject today. So trapping the light inside the solar cell. And you are having an anti-reflective coating to decrease the light reflection and more. Then you are having the contacts from your solar cell. And the main idea is light-matter interaction. So light comes and interacts with matters and creates electron hole pairs inside the semiconductor. And after this absorption generation, you are having separation of these charge carriers because electron is negatively charged, hole is positively charged. So they are separated through this semiconductor junction. And then through the contacts, metallic contacts, you collect these electron hole pairs and send them to the grid, and you get electricity power extraction from your solar cell. And in the surface of this solar cell, you are having this light trapping texturing structures, which is the main idea of our talk today. But I would like to say also this anti-reflective coating, for example, is optimized for this photovoltaic black body spectrum that represents the sun, which can be considered as a black body at around 500 kelvins from the first talk. Mainly for a good solar cell, you have to do a lot of light management and optical engineering to get higher efficiencies. Optics is always involved in photovoltaics, I would like to say. So light trapping in crystalline silicon, you know, crystalline silicon is not a good absorber. It has an indirect band gap, so it does not allow, it does not absorb light easily. So when you have a flat silicon, you can see that light coming into the solar cell can easily escape the solar cell without any path length and enhancement, as you can see here. But when you have surface texturing in your solar cell, front of your wafer, as you can see in the monocrystalline silicon, you have path length enhancement because light coming into your solar cell is totally internally reflected in the solar cell, like the ones in the fiber optic lines, and then it escapes, and it takes too much time inside the solar cell and increases the absorption probability. And you can see for monocrystalline, you are having this pyramidal surface structures. And multicrystalline silicon solar cells, you are still having the path length enhancement, but not with pyramids, but some different structures, some random structures, and micron size structures. As I said, path length enhancement by total internal reflection and decreased reflection by multiple bands effect. And now today I'm going to talk about multicrystalline silicon because we have the problem there, not in monocrystalline silicon. Industrially speaking, wafers are cut from ingots using one of the two methods, slurry cutting or diamond cutting. Slurry cutting, based cutting results in a homogeneous surface crack distribution in the surface of the wafer, and kerf loss is high. Kerf loss means when you are cutting wafers from ingots, you are losing some silicon powder, and this is a loss and it has to be decreased. And diamond wire cutting, on the other hand, results in a rather smooth surface with unevenly distributed cracks, and kerf loss is low, and diamond cut wafers are cheaper. Mainly, I can say that when you have a slurry cut wafer, you have this matte surface, while when you have a diamond cut wafer, you are having this shiny reflecting multicrystalline surface. And industry is always asking for diamond cut wafers, so we have to use diamond cut wafers. But when you try to texture diamond cut wafers, normally you are using hydrofluoric acid, nitric acid, and hydrogen peroxide for texturing these multicrystalline solar cells, but this method is sensitive to starting first surface. When your surface is rough, you can have this texturing easily. In the slurry cut surface, this texturing method works. But when you have diamond cut surface, you cannot have this working well because you are having polishing or inhomogeneous texturing in your surface. So diamond wire zone multicrystalline wafers cannot be isotextured effectively. That's mainly what I can say. So what can we do? We can use plasmonic scattering, laser texturing, plasma texturing, reactive ion etching, photonic crystal scattering. Some of them are photonic structures that work. Plasmonic, for example, or laser texturing again uses light to interact with surface, and reactive ion etching to make some black silicon. But all of them are low throughput vacuum processes or small area applications, they have some time to get industrialized, as Alpan just said. Now they are mostly on laboratory or pilot level. They have to be industrialized, but metal assisted etching, which is a solution-based method, is an easy to implement method and applicable to large area and batch process, which is high throughput, and it's a top-down approach. So you can control the electronical and mechanical properties. As I said, this is a chemical method. You can make batch process, high throughput process with this. So this is a potentially good method for texturing. And you can engineer the surface by using nanowires, nanoholes, nanocones, microwires, lamp structures, etc. So what is metal assisted etching? Mainly you are using a metal to etch silicon surface. So you deposit some noble metal on the surface of silicon through some metallic salt, noble metal salt like silver nitride. And the silicon underneath this metal is oxidized faster than the areas where there is no metal conduction. And then this oxidized silicon is etched by hydrofluoric acid easily, and this metal sinks. And as this process continues, the metal sinks more and more, and you can have these hole structures on the surface of your silicon wafer. And by optimizing the solution and chemical properties, you can have a wide range of structures on the surface of your silicon wafer. What are these structures? For example, nanowires. You can have 20, 30, 40 nanometers radius nanowires on the surface of your silicon wafer that are long, like 2 microns, 4 microns, 8 microns, 10 microns. You can have nano holes on the surface of your structure. You can see nano silver going through silicon and making these nano hole structures, or you can have nanoconic structures, which is different varying radius throughout the surface. So you can have all these different structures, and since they are having nano texture, nano nature, they are in the nano sized part, their reflection properties are perfect. They nearly reflect none of the light coming to them, and they are called black silicon. Normally, when you texture a silicon with standard texturing methods, it's mainly dark gray at most. But when you use this nano texturing, due to this pad length enhancement, and also due to this index match, you can have highly non-reflective surfaces that's called black silicon, and that's what you can achieve after this nano-texturing methods. And normally, when you have a slurry cut multicrystalline solar cell, your process is like texturing, doping, junction isolation, passivation, anti-reflective coating, and metallization. But when you have the diamond cut multicrystalline solar cell process, because you want to decrease the cost, you want to use diamond cut multicrystalline wafers, but you cannot use isotexturing. You just add a metal assisted etching bed in front of your isotexturing bed line, so that the surface is nano-textured by your metal assisted etching bed, and you easily make your surface rough enough to be able to use isotexturing. So metal assisted etching is a precondition, can be used as a preconditioning step to texture your industrial wafers, and it creates etch pits on the surface to enable initiation of the isotexturing. And I would like to state just a reference to the first presentation again. In our factory, also in industry, doping, metallization, parts of standard crystalline silicon wafer processing, we are using lasers, high-speed lasers. So lasers are everywhere. It's also in crystalline silicon solar cell manufacturing. So we are not also only using light to we are not only producing devices that uses light to generate power, but we are also using lasers to produce such structures. So it's an important part of our processing steps. So this was my PhD thesis, metal assisted etching, and later on it became popular also in the industry, and there are also even machines that are using these structures, this technology to make solar cells, industrial solar cells. And when you see when you look at the forecasts, around 30% of the market is using multicrystalline wafers, and they are always going to use diamond cut multicrystalline wafers. And you can see metal catalyzed chemical etching is going to be suppressing, dominating the multicrystalline solar cell market. So this application of nanotechnology on the surface of crystalline silicon will be more popular and more applicable in the future, in the coming 10 years, according to the forecasts, I can say. So in summary, I can say texturing is required for PET enhancement of crystalline silicon photovoltaic cells. We are using light and we want to use it as effective as possible. So we want to increase the PET length inside silicon to get more absorption. And monocrystalline can be textured independent of the surface condition. Thanks to crystalline structure, you can see pyramids. They form always on the surface of monocrystalline solar cells. But since multicrystalline solar cells don't have an homogeneous crystalline structure, texture and performance depends on the surface finish. And diamond wire cutting is advantages in terms of manufacturing costs. Diamond cut is cheaper, and industry always wants to use this, and it's not suitable. You cannot use this wafer with this texturing method, so you have to find a new method to manufacture diamond cut multicrystalline solar cells. And here the solution to this problem, one of the solutions to this problem, is metal-assisted etching. Metal catalyzed chemical etching is an industry applicable nanotexturing method that enables multicrystalline texturing on diamond wafers on wafers. So with these nanowires or nanopits or nanoholes, you can have up to black silicon surfaces, even if you are having a diamond cut surface. This is a solution for this problem, I can say. So mainly this also shows maybe an answer to one of the questions. Some technology so metal-assisted etching is found by someone in the laboratory and it's developed. Then some researcher uses it, and some researchers, not only one, thousands of researchers uses it to apply it for different structures, for example, like solar cells. And then after it's proved, it can be used in industrial applications. So all process steps are done in academic, laboratory, and industry. And this is a good example of this. And with this, I would like to celebrate this International Day of Light of everybody, and thank you for your attention.
Thank you, Hocam. If there is any question, we can take them. You can also ask your questions via chat. So while waiting, I want to ask something. As I know, the efficiency of the solar cell depends on the p-n junction. Am I wrong? I think p-n junction limits the efficiency.
Okay, I was muted. In fact, as I showed in the one of the first slides, absorption, generation, and collection. So there are different losses. For example, optical losses. When you, if you have a good electrical quality, then optical losses are the dominating losses. But if you are having a perfect optical enhancement and no reflection, then of course electrical properties are the dominating losses. And then in the electrical, you can have recombination losses or resistive losses. These also have to be optimized. So we cannot just say p-n junction is the limiting one, but each of these losses are important. Of course, when you have crystalline silicon, of course, due to the band gap, you are having some theoretical efficiency around 28, 29. You cannot go above this with crystalline silicon only. You have to use different materials like tandem devices or different band gap materials. So not only the p-n junction, but it as a whole, there are dominant and other loss mechanisms, I can say.
Okay, any question?
Can I ask a question?
Yes, Tarek.
Hear me, right? Talking about solar cells, I'm not that much special about that. Like I don't have much information about that, but dealing with solar cells, they can, like, after some time decay or lose its efficiency somehow due to the texture on the surface of it, or humidity, or other things. How you can solve this problem faced by the outside circumstances?
Thank you. First of all, yes, we are losing some efficiency within years when it's on the field. First one is due to the, as you said, for example, the glass can lose some of its transparency. The coatings on the surface of the glass, anti-reflective coating on the glass, can be damaged, and the polymers inside the module lamination lose their transparency due to UV light. But also crystalline silicon itself under light loses some of its efficiency due to some boron oxygen related defects that get activated under light, and also under temperature, operating temperatures around 80 degrees. We are having some internal losses also. All this can be engineered and can be dealt with. For example, non-UV blocking, or the polymers that you are using, if they don't get this yellowing throughout the years with some kind of chemistry inside, you will not have any transparency losses within time from your solar modules. But of course, your glass is open to air, and the anti-reflective coating on the glass will be damaged. This is inevitable due to humidity, due to dust, due to other physical effects, like birds are flying and they are dropping their dirt on the modules. So, such kind of things are always affecting your modules, and you have to make better coatings, high efficiency and long lasting, and high mechanical properties, high optical properties, thin films to get rid of these effects. But in the end, you will lose. But this, how much you lose in that, in 20-25 years, you are just losing 20%. And after this 20% loss, for 100 years, they say it's not measured yet, but it will not lose its efficiency anymore, and it will be stabilized at 80% capacity and work in these efficiencies. So we can mainly say that.
Does these numbers, like, of the years for general solar cells, or it has like different thing? Because some of the solar cells have different microstructure, nanostructure, where it loses this kind of efficiency easier than others. So is this number for like the normal silicon, crystalline silicon solar cells, or is it general, like, how I can say it? When we have a structure, which is nanostructure thing above the silicon, these kind of things, I hear that it decays easier and faster than others. That's why many people say, like, the future of solar cells is not that much. So I want to move my question to the potential of solar cells for the future, as we are talking about the International Day of Light, and light is the, like, renewable energy that we are looking for. What do you answer these kind of question of the future or the potential of solar cells?
In fact, when you make the solar cell, solar module, your solar cell is inside your module, and it's encapsulated by ethylene vinyl acetate, some kind of polymers, and then the glass and the frame. So the solar cell is not exposed to air or anything, but the glass outside. So glass is taking all the damage from outside, So whether you are having a nano texture or a micro texture or no texture on the surface doesn't matter. You cannot have any decay on the surface with your nanostructures. Of course, when you have these nanowires on the surface as a solar cell, and if it's exposed to outside conditions, these nanotextures will be affected more. But mainly in real life, they are not exposed to outside, so there's no difference between nano or micro texture on the surface. But nano technology, I can say the main the technology is going towards crystalline silicon, monocrystalline silicon, not multicrystalline. And for monocrystalline, mainly pyramid texturing is the effective one, which we cannot use anything else. It's the best one until now. And perovskites, which is a new method of solar cell production, which is a new material, they're also being developed and being studied. Research is done extensively on these solar cells, and I also believe that in the coming 10 years, silicon and perovskite tandem, or if perovskite is not successful, some other material that will be tandemly used on top of silicon will be the future of crystalline photovoltaic industry.
Thank you, Hocam. There's a question in the chat. Idil thanks you for the presentation, and she also asks that in KalyonPV there are 4 completed projects and there are other projects that are currently progressing. What are the projects about? Please.
Okay. Mainly, as I said, some of the projects are directly focused on increasing the decreasing the cost per watt of our solar cell. What does cost per watt means? The cost of producing a solar module. Either you increase the module output, power of the module, by increasing this, optimizing its processing sequence, or decreasing the costs. Both of them are some optimization processes. So mainly research is done on cost considerations and also increasing the efficiency of your solar cells. But also, as I said, localization projects, which means that mainly you have to buy most of your chemicals and other materials from abroad, from China or Europe. But since the sector is developing in Turkey and we are a big manufacturer, we are purchasing lots of materials, and as R&D center, we are trying to develop these small manufacturers to develop their technology to produce these materials for us, so we can buy them from Turkey and easily, and they will serve to the other factories also in the future. And also recycling and waste management projects are also going on. As I said, we are having a lot of chemicals and chemical waste, and we are processing these wastes. We want to use them again, or we don't want to harm nature, so we are doing R&D on these subjects to have a cleaner production and more efficient production. And also new technologies, as I said, tandem structures and other kind of new technologies, IBC or N-type technologies. We are also working on these technologies for future.
Thank you, Hocam. Are there any other questions? Okay, if no, I will ask something. I asked about efficiency before. Now you showed pyramid shapes on the etching and nanowires and nanoholes. Which one was the most efficient? I mean, which one did you continue your production with?
It was my PhD thesis, and mainly pyramid texturing for monocrystalline is like the upper limit. It's one of the best texturing methods you can achieve. So it's not easy to compare your nanotexturing with them, with pyramids. Of course, during my PhD thesis, I managed to have higher efficiencies from my nanotextures than pyramid textures, but it was a special process, just optimized for my structures. mainly for industry, for pyramid texturing. You cannot use nano texturing instead of pyramid texturing. But when you go to multicrystalline, then it's you have to use another method than this microstructures, and there comes nanowires, and there nanowires show their potential. They are having, at least you can texture your surface and you are getting higher efficiencies. And when you compare the nanowires, nanoholes, and nanoconic shapes, I found in my thesis that nanoconic shapes are having the better optical properties and electrical properties, because when you have nanowires or nanoholes, your surface area is getting very high and you are having a lot of surface recombination. So when you have conic surfaces, both your doping is more homogeneous and you are getting a lower surface area. So you are earning from optical properties, but you are not losing too much from electrical properties. So I can say nanoconic surfaces was the best one throughout these nanotextured surfaces.
Thank you, Hocam. Okay, as I remember, we had a photonics break event just like this one, similar to this one, and Rashid Hoca was invited to that, and he talked about this, and I was wondering actually since then, so this answer solved my problem. Actually, thank you so much.
Thank you very much.
Okay, any other question? There is another question in chat. Ihsan asks, maybe it's not directly within your knowledge, but I wanted to ask, he says, when you look at your competitors producing photovoltaic panels in the sector, do they keep profitability more at the forefront, or do they keep the product more efficient than the products in the market? I ask this to understand how much importance the industry places on research and development.
In fact, both cost and efficiency are very important. Time to time it differs. For example, when you have some material shortage in the market, like around 2010, there was silicon crisis, so it was hard to find polycrystalline silicon, and material costs were high, and there the material cost reduction was the dominating parameter that affected the cost per watt. But for example, nowadays, at least the last 3-4 years, I can say material supply was more than enough and costs were lower. So most of the work were done on efficiency enhancement. So that's why the sector is always going on the monocrystalline, which has higher efficiency. Nowadays, I can say it's more on efficiency enhancement side rather than cost optimization. This is not only for cost per watt, but also crystalline silicon is reaching its theoretical limit. As I said, it's 28% around, and practically it's said that 27 will be the final for industrial cells, and 26. Around 26% is already demonstrated on large scale on laboratory, and on industry, on N-type, we are having 23.5%. So in 5 years, most probably we will be reaching the theoretical limit of silicon, and research and development comes here because you need to find a new way to get away with this theoretical limit. So, but for research and development, you don't have to always think like increasing the efficiency, but also cost reduction is a big problem of R&D that we are trying to solve in our projects, like decreasing the usage of silver on the surface of silicon, or using less polysilicon per wafer to decrease the material costs.
Sir, if we decrease the thickness of the solar cell, is it possible to increase the efficiency?
Of course, up to some point, electrically it is very good, and also for cost saving, it's very good. But of course, there are some drawbacks. First, when you decrease the cell thickness, then you are having a lot of transmission. You are having transmission losses. You have to deal with them with better light trapping. And also when you decrease your cell thicknesses, production gets very harder. You are having more breakage in your factories. So even decreasing the cell thickness from 180 microns to 170 microns results in very high yield loss, very high breakage loss in our factory. We are now working on decreasing the wafer thickness, but even 10 microns is very hard. But mainly, of course, ideally with a very good light trapping, it is always better to have thinner wafers.
In most ideal cases, what would the limit? If you have a silicon wafer, what would you suggest to be the thickness of this wafer?
In fact, I cannot directly say because I cannot remember right now, but mainly down to 50 microns, the standard texturing methods are very well welcomed. And if you are having good light trapping, you don't have to care about thickness, and if you can process it in industrial scale, you don't have to think about the thickness.
Okay, thank you.
Okay, there's one more question in the chat. It says, I assume that when solar cells get old and lose their power, their efficiency, they should be replaced. If so, how recyclable are the solar cells? I'm so sorry.
In fact, as I said, they are getting old, lose their efficiency, but in 20-25 years, they can be installed in the field. You don't care about the losses because they are still economically feasible throughout these 20 years. But after this, they lose their economical life efficiency, and they have to be replaced. But recycling is not very well developed yet for the solar cells. You are having glass, you are having plastics, you are having silicon, you are having some small amount of silver on the surface. But recycling systems are not very well developed for the solar modules right now. People are working, we are also working on this. Since it's a new technology on industry, no one reached its 25 years of field lifetime up to now for an industrial commercial project. So there were no need until now, but in 5 to 10 years, this kind of processes will be developed also. So it's a new area of, I can say, industry. If you want to work on it, it's a good opportunity, I think.
Thank you so much, Hocam. Are there any questions? Okay, I think no. Of course.
I was gonna ask how the research process during the pandemic was like. Did your working efficiency decrease during the pandemic, or was it the same? How did you go through this time?
Of course, we cannot lose our efficiency throughout production because it's a commercial production. It's the company has to have profit, so efficiency did not decrease. Pandemic did not affect so much us because we are still working 3 shifts and we are going to work. We are not having this home office thing. We are working in the factory because it cannot be stopped. We are having this. We have to have this line running 24 hours every day. But of course, the costs and material supply is very challenging, and costs are getting higher because due to pandemic, some materials production is decreased and we cannot find easily. And mainly it affected the cost, not the efficiency itself.
Okay, thank you.
The majority of the questions were about the efficiency, either working or the power efficiency. It's very important. Okay, are there any questions? Okay, if no, thank you so much for the speech, for the presentation, and coming today, celebrating the Day of Light with us.
I thank you very much. Thank you for you.
We are so happy to have you today here.
Hello. Before leaving the stage for you, Alkan Hocam, I would like to introduce your early career and your early education. As I see that you were an undergrad and a master's, you were studying master's degrees in University of our university, in Middle East Technical University. In that years, in 1998 and 2000, between 2002, you were graduated from our school as an undergraduate and with an high honors degree. And after that, you were a master's degrees. Immediately you studied master's degrees also in our university and also in physics, in physics department. Then you moved, and Alkan Hocam moved to University of Southern California, and he changed his department to Electrical and Electronics Engineering department and studied master's degrees. And after that, he studied a PhD, also in Electrical and Electronics Engineering department. And while his years in University of Southern California, he was a research and teaching assistant. After that, he became a research scientist. And then in 2019 and today, he is a senior optics engineer in Alkan. I hope I pronounce it well. And also yes. He's an adjunct lecturer in University of California.
Yes, yeah, that's pretty nice summary. Thank you, Halit Hocam. Thank you very much. Yeah, so may I start my presentation then? Let's see.
Yes, the stage is yours.
All right. Yeah, currently, I'm in Alkan, Fort Worth, and my talk, but my talk is going to be concentrated more on advanced beam shaping and spatial emphasis on computer-generated holograms. This is another summary of my past. So I graduated from the METU physics department, and I got my PhD in University of Southern California with my thesis on computer-generated holograms. Then I worked on holography and lasers in Luminate as a research scientist, and currently I'm working in Alpan, designing intraocular lenses and also giving some lectures in the University of California, Irvine. So this talk is compiled from some OSA and SPIE presentations. And mainly it includes my PhD work and some of the US government projects, which are open to public for sure. And these are all about manipulating lasers, manipulating beams, actually. Basically, it's about controlling the light. So when you control the light, actually, this is what you want. You control the energy. Okay, so this slide is a very brief summary of advanced light shaping. Actually, definitely you can give some more examples on that, but mainly when I say advanced light shaping, it means diffractive and refractive. both diffraction and refraction come into play, and the light can be laser or can be sunlight or any kind of light. The problem is that you are given a light source and you want to shape the light as you want. That's the ultimate goal. For example, if you look at intraocular lenses, which I'm not going to talk too much today, but I will just give a very brief summary of what it is. Human eye has a lens inside, and it's flexible. It can change its focus. So there are cases that you lose your lens when you have cataract or presbyopia kind of illness, and this is very common. When you get old, you are likely to lose your lens. But when this happens, don't get scared, because there are artificial IOLs, intraocular lenses. If you go to doctor, then they will just replace this half-an-hour surgery. So these lenses can imitate the original human eye lens. As you see, this lens here is using refraction and diffraction both together to create multifoci. So this is, you can see, two foci, which is used by the eye to both focus for the distant and near. So currently we don't have a completely flexible lens like nature does, but we have a multifocal lens which enables you to see both distant and near objects very well. So we owe this technology to the refraction and diffraction together. So this is a big research area, and it's very, very profitable, and a lot of companies. Alkan, I'm working at Alkan. Alkan is the leader for this area, and there are other companies as well. So computer jet holograms is what I'm going to talk today. It's basically a the computer generated holograms are just wavefront shapers. So this is completely diffractive, and you can combine with refraction as well to create a lot of nice things, which we will be talking about today. And on the very right, you can see holographic optical element. This I put it because it's very common now. It's very popular. I suggest you to visit one of those SPIE conferences. It's generally held in San Francisco in February. So they built like see-through displays, like 3D, scene generators, and especially Facebook is investing a lot on this. So basically, this is a lens, but this is a holographic lens. We can just simplify by saying that it's a holographic lens. So why this is different? Because this is a see-through. See-through means you can also see the scene. Like you can put it on your glass and you can see everything well. But this lens has a special angle to reflect and operate. So only this angle it operates. So this gives us a lot of opportunities to create display options. A lot of displays can be done with this technique. So this is a lot of people think that this is the future technology, and Zuckerberg is investing billions of dollars on this currently. But yeah, let me continue with this computer generated hologram stuff. Okay, let's go with the. All right. Okay, so and this slide just summarizes the principle. Basically, it's a CGH, a computer generated hologram, contains lots of diffractive structures, as you can see. This is a fully transparent piece of glass or piece of plastic, supposed to be fully transparent. Definitely there are losses, but supposed to be fully transparent. You can also use it in reflective mode. So in this case, we have diffraction from several locations. And if you engineer in a smart way, you can get a 2D or 3D image at the end. Actually, you can consider this a faceplate, which can shape the wavefronts. So let's a little bit more technical details here, how to design. There are different ways of designing these structures. But if you consider the simplest example, we have a lens for easing the imaging, and we have an image we want to reconstruct. So basically, you design this diffractive structure to create this image. So the image you can consider in the broadest sense that you want to control the beam. It doesn't have to be. It doesn't have to be a image. For example, Apple using the CGAs in the cell phone. So when you have face recognition system in your phone, it means a lot of beams are shining through your face. You don't see them because they are in IR, infrared region, but they are engineered so that they just create a pattern on your face, and with the back reflection, the telephone, your cell phone can detect your face. So there are a lot of applications. So you can consider this image as a desired waveform, whatever it can be. So broadest sense. So in the design, we can just propagate back and forth, and in each iteration we impose the image information onto the beam. So you iterate forward and backward directions, and each iteration makes your image much better. So if you notice on the left side, we don't have intensity modulation, only phase modulation. So intensity modulation is not desired for a lot of reasons that I'm not going to get in today, but only phase information you can create this image very well with this iteration technique. Okay, so this is my PhD thesis. Well, it was given in the USC, I think, at the end of 2013. So in this case, we investigated multiple CGH stacks. You can see they are separated with some distance, and on the right hand side, we can see a lot of images. These images actually you can consider as a 3D image, right? So 3D image, you can just divide them plane by plane. And we asked the question, so how can we improve the 3D imaging with these cascading structures by also expanding these structures? So these structures on the left, you can see we expand them both X and Y directions. You can see the red square, but the other side, we are expanding these structures. Also, we are expanding in the Z direction. So there are N CGHs here. So the expansion in 3 dimension on the left, and on the right, again, we have a 3D image. So this was published in several papers and conferences. Let's see a little bit more technical details about how to optimize this structure. So in this structure, I put the propagation operator here. It's a Fourier propagator we can consider. And here, how to propagate between the different elements. Basically, you pass to the Fourier domain first, then you propagate and get back to the spatial domain with inverse Fourier transform and multiply with the next element. Yeah, this is the super simple summary of the mathematics. And on the right-hand side, I put the structure of the algorithm. The algorithm is similar to this one, but it just expands. You know, you calculate each CGH one by one. So basically, if you are interested, I would suggest you to go to this paper, the one in Applied Optics, for more information. So I don't want to get into too much details about this algorithm, but basically it's straightforward, and but it requires some care to apply on this structure, on this system. Okay, so let's see the results here for this. So on the right-hand side, let's start with the right-hand side. You can see the 1 and 2 numbers. These are images, okay? And you want to reconstruct at some level here. So you want to reconstruct in space, okay? So on the left-hand, on the at the bottom, you see the result of this image reconstruction. So the left one is the 1 CGH result. And on the right, you can see the 4 CGH result with some more extension in the XYZ direction. So you can see the noise is really lower now. So left side, we show the graph. So the K direction, it denotes the spatial expansion, XY direction. So when you expand your system, so K means here, so you have now larger CGHs, larger CGHs. Here from 1 to 2, 1 means the same, 2 to double, and n means the number of elements here. Say the number of elements. See the if you consider the K axis, it decreases. Also, that also decreases with some amount, and the result, it never gets to complete 0 because we are killing the amplitude information. There is no amplitude modulation here. So theoretically we cannot get perfect image, but we can be very close to it. Very close to it. So yeah, this is the summary of one application of CGHs, image reconstruction, and this is very important research now, and it can be used a lot of places. For example, LiDAR is using that technology. So let me pass to another topic now, again related to computer-generated holograms, but now we're applying to somewhere else. This was a part of a government project, which is open to public, and it was published and patented and presented in a lot of platforms. But I will put just a summary here. In this case, you can see the slide. You can see a laser cavity. At the bottom, the real laser in the lab, and on top, it's the abstraction of the laser cavity. You can see the mirrors. You can see the laser crystal, the pump. It's actually a diode pump solid state laser. So diode is pumping the solid state and it lasers. The laser characteristics are given here on the right. So this is a not very high power laser, and it was built for experimental purposes. But this is the crystal is an orthogonadate, neodymium doped orthogonadate laser, and it's giving out 1064 nanometer output, infrared range, which is pretty interesting for a lot of applications. And it's pumped by 808 nanometer diode laser. So this is our laser, and currently this is what we have, and we're gonna talk about how we can improve this in this part of the talk. So let's see the laser characteristics, the laser operation performance. Please look at left side. You can see an image. So if you took optics courses and if you made research on lasers, you can recognize this is a TM00 and TM01 mode, and the M squared is 4.6. So let me clarify a little bit. If you don't know too much about the M squared thing, it defines the performance of the laser. Like for a laser, we dream the best laser is the one which diverges least with the maximum power. So as a rule of thumb, the bigger power you have in a laser, the more divergence your laser is. But this is not desired. You want a high power laser with minimum divergence. So on the right, you can see the definition of the figures of merit of lasers. M squared is the beam divergence, and brightness figure of merit also takes the power into account, also the efficiency figure of merit. So you don't have to worry about too much. So I don't want to give too much detail, but you can consider this as a ordinary lasers output. You can see with some figure of merit. Is this good? Depends on your application. But it's just a basic laser, so there is currently no R&D, no innovation for now. It's nice to see. In fact, when we saw this laser first, we were very excited. But there would be much more to get more excited about. Okay, so let me take you to some mathematics here. I found this stuff pretty exciting as well. On the left top, you can see a very abstraction of a laser cavity. You can see the components, and every item has a mathematical operator. You can see them, all the operators. You don't need to worry about the details, but it works pretty well if you construct this laser. So my aim was here to simulate the laser cavity. So in order to modulate the laser cavity, you need to simulate. So you can see at the very bottom, you can see an eigenvalue equation, and I thought the eigenvalue equation was only for quantum mechanics, but it actually works pretty well with the laser cavities. It's a huge topic, so I cannot talk too much. I want to, but let me say that it's really exciting thing to define a laser cavity with an eigenvalue equation. So this equation is only thing you need to mathematically define this cavity, and then you can simulate your cavity as you want. So okay, here you can see a CGH came into the play now. So why do we put this CGH here? We want two things. First, we want to get rid of this curvature. Okay, so see the curved mirror. We want to get rid of this, and we want to improve the mode quality. We want to improve the laser figure of merit. So we put the CGH here. This is our new laser cavity now. Okay, so we define the laser cavity like this, and we calculate the structure of the CGH. So the structure of the CGH is calculated by simulating the laser by using this formalism. This is actually pretty much electromagnetics theory and applying all the operators, and it's a little bit advanced application, and but it's pretty doable. It's you know, kind of straightforward if you know the basics. And then you can calculate the CGH structure with this equation. This equation is actually, this takes the concept of mode. A mode is a structure that is stable in the resonator, a laser mode. So when you have a laser mode, you can just calculate your CGH by making the, you know, the simulations. And you can impose the CGH, which mode you want to have. Okay, so for example, you can design your CGH to get a single mode, Gaussian mode, for example. So this mode is not good for us because it contains two modes here, TM00 and TM01. But this is not good enough for us. And after the CGH, we improve the laser cavity, and let's see the results here. You can see the CGH here again. This is a this is all transparent CGH with some parameters. You can see the pixel size is pretty large with respect to imaging. Imaging CGH is a pixel size you require around 2 microns, but this time you have like more than 10 microns pixel size. And at the bottom you can see the performance comparison. On the left you see the old ones, the old laser output. And on the right, you can see the new one. The new one is the Gaussian. Yeah, you can recognize the Gaussian mode here, and with the pretty good improved beam parameters. So the beam parameters are pretty much improved with this operation with the usage of CGH. That's what I can say as a summary for this. And if you have questions for this, definitely we can discuss after that. But currently, let me finish this project, and let's pass to the next one. So more exciting topics are coming. This is another big project, and this is very common with the LiDAR. So if anyone wants to work on LiDARs, you can find this exciting, because in this case we have a beam. We have a beam coming from here to the CGH, and at the end you have a uniform illumination. So uniforming the illumination is a very big topic in illumination industry, in lighting industry. So yeah, we use the CGS for this, and we have the divergence angle. Definitely we have some boundaries on this. So the larger the angle, the harder the life is, as you can predict. So the far field of the CGH, if you have a lens, is basically Fourier transform. So nature was pretty generous to us in this case, because you just take the Fourier transform and find the image. In the simplest sense, definitely there are too many complications, but in the basic format, it's kind of simple, because you just take the Fourier transform and find the image. And by the way, for the optimization of the CGH, how to make this, remember the first slide, you know, the iterative Fourier transform algorithm. Remember that one is the main thing for optimizing almost all of the CGHs outside the cavity. But for inside the cavity in the previous project, it's quite kind of different. So this is a real example coming from our lab in my past company. So you can see it's just a green laser. Here, I want to show you the green laser is here, and this is the CGH, and this is the uniform beam. See how cute it is, how uniform it is. It's pretty bright, and it's pretty uniform and stable. This is another application, and as a final application, this was a very exciting project I worked on. It's for an agency, and they said we are examining chips, but we want to make some marking on them. So it's called fiducial marking. So basically, you have some chips or whatever component, but you want to put some marks on it. You know, it's like printing on a solid surface. So for this purpose, we propose to use CGHs. But the working principle is very similar to this one. But in this case, we have the Fiducial Mark. Here you can see the optical setup. We have a collimator, we have a CGH, we have an imaging lens, and we have the silicon substrate. So the fiducial marks on this can be seen on the right. So we use the pulse laser for this, and it's kind of a high power application. And you can see the dotted structure. Each dot is one image to create the fiducial mark. The fiducial mark is, you can see the complete structure, the four crosses, the signs, and at the center there will be the chip. So this is the fiducial mark, and it was done with the CGH. Definitely you can make a normal imaging system, but normal imaging system has some problems, like for example, it's very sensitive to distance, and for very small apertures you have the diffraction effects. But CGH only works for diffraction, so no problem for it. So let me conclude with this slide, and then I think we can pass to questions about my talk. So I tried to explain some novel applications of computer-generated holography in light shaping applications from industrial and R&D domain. Computer-generated holograms are very innovative light shaping components, can be used in anywhere, like displays, optical interconnections, optical inscriptions, 3D imaging, LiDAR, and too many other areas. So yeah, I believe the future of optics is very bright. And again, thanks for inviting me to here. It was a fun for me. It was an honor for me to talk. Thanks for listening.
It was from Ihsan, and he said, in this section, does the design of the Fourier transform lens system require a lens that requires a fixed design or a specific design for each CGH?
Okay, so the lens, no, the lens is standard, but you need to if you're using lens, you need to place your screen at the focal length, okay? But you don't have to use a lens. For example, in this case, there is not a lens used, but the distance is so large that you don't need a lens for a very large distance. For the shorter distance, you need a lens, and you don't need a different lens for any CGH. Just any lens, as long as you adjust the focal length. Yeah, for the CGH, every CGH has its own illumination pattern. So for example, for this one, it can only be used for that kind of image. So yeah.
Thank you, Hocam. I have a question. We invited other speakers talking about imaging before, and we always listen speeches on like imaging through something. So this what you talk about is kind of a new topic for us. You use imaging to create what I couldn't exactly understand that part, but I think you have a cavity, but you use CGH imaging and you create a new cavity according to your will. Is that correct?
Oh, okay. Let me explain. So basically, okay. Okay, for this slide, okay, imaging is not a perfect word, I would say, because imaging means there's an object and you image to somewhere else. This is traditional method, but in this case, I just, okay, there's an input beam coming to the element, and I just manipulate the beam to create the image. Okay, so yeah, it's kind of imaging, but not in a traditional sense. So I just, let's say beam shaping. Okay, beam shaping. For this one, okay. For the I think you asked the intracavity. Intracavity is similar in philosophy. It is similar. Okay. Intracavity is different. In intracavity, there is no imaging. Okay, there's no imaging. So in a laser, light beams come and back and forth, right? And in each pass, they are shaped by the CGH. So there's no imaging here, but they are shaped by the CGH to shape the modes so that you end up with the desired mode here, okay? That's a little bit different, but thanks for asking this. I think this is a good point to emphasize, yeah.
Okay, Hocam, thank you. There is another question in the chat. Isan asks, in this case, I guess CGH can actually produce only one pattern. So we can't create a pattern we want instantly, like DMD, digital micro device.
Yeah. Thank you. Yeah. So yeah, that's another. Okay, let me take you to here. Let's talk about it. Okay, so see the final bullet here. Reconstruction is fulfilled with a device realizing the diffractive optical element or with a special light modulator. So let's talk a little bit more about that. So what I presented here so far is mostly DOEs, like a static, because most of the applications require like a static DOE, you know, but like for the 3D displays or things like that, it's not good, right? So because you need a dynamic image. It always changes. So then you have to special light modulator. There are micro special light modulators that, you know, the scene is dynamic. So it keeps on changing. Like you can consider this, the CGH, but every pixel is changing in microseconds. You know, there are special light modulators or micromirror device. This is called digital micromirror device, mainly fabricated by Texas Instruments, but like Hamamatsu, lot of dynamic displays you can find, and most of the cases actually they are used in reflective mode. So again, we can categorize. In summary, we can categorize this in terms of the optical operation. We have transparent and reflection, which I showed here. The transparent operation. In terms of the, you know, the let's say movement or the scene generation, there are again two types. the static ones and dynamic ones. Again, I presented here the static ones, but other versions are definitely available. Yeah.
Thank you, John. Any questions?
Will the structure be the same if we use SLM, or it has different kind of design?
For which one? For this?
Generally, we put like the CGH in the cavity itself at the second mirror.
Yeah. For the laser cavity, no. For laser cavity, this one. No, this is DOE, not SLM. This is a because inside the laser cavity, I haven't seen any SLM used because it's not very profitable. Because for a laser output, here you don't image, you just basically manipulate the laser beam to get the best. You know, the needs don't change. For the image, the needs change because you want to watch a 3D movie, for example, right? Things like that. The need change, but for laser modulation, your need never changes. You always want the Gaussian beam, right? So that's why you can keep the CGH in. This is static, you know.
Okay, there is another question in the chat. Do you have a sample device for CGH application in devices like VR, a product that has reached the end user?
I do have. I do have some, yeah, definitely. For example, okay, I think they're asking VR kind of things, right? For VR kind of things, there are few, but let me give more information about the chimcell. So chimcell is a word used for the stoplight of car. So we had customers to make stoplights. So basically, this is a little bit different, but it's good to know this. So you have a car, right? You have a car, and when you press the brake, your stoplights turn on, right? That's it. But consider that you put a stoplight at the back, at the rear window. You have a big stoplight, okay? If you put a big stoplight, you cannot see back in a usual application. But in this case, this is invisible, but it still turns on. This is a kind of VR application. I'm not sure if I can explain good, but let me try maybe. Okay, yeah, the structure is similar. Okay, let me show you. The structure is similar to this. Okay, so there's only Bragg angle, which creates the light throughput. And for example, in this case, we put it on the back, on the rear window of the car, so that when the driver wants, there's a stop sign illuminating. But normally the stop sign is invisible. So this is actually a VR application. Other than that, we definitely make some helmets for different applications. And in the past, some government agencies were our customers. But the VR application is very similar to that as well. The logic is the similar. Although there are other approaches from different companies for this, but I think it explains. Yeah.
Thank you, John. Can I ask? Oops, sorry, the question goes on. So on the road, we will suddenly be able to see a big stop sign in front of the driver, in front of our eyes.
Yeah, just get prepared to be surprised. I mean, future is coming with optics, so you can see a lot of fantastic things. Actually, you can still see. As I said, I went to one of the conferences in SPIE, Optics Photonics, AR/VR conference. I strongly suggest you to attend, but I don't know what happens after this pandemic. But it was really cute, very beautiful. And believe me, they will surprise you. They will surprise you. Yeah, there are a lot of interesting applications with this. But definitely you cannot beat the fundamentals law of optics, the physics, but you can really extend, you can really push. And for those who are interested in this, I would suggest topics of metamaterials, nano-optics, because when you get down to, smaller than the wavelength, a lot of new things, new effects come up. So you can also study on this field to make more innovations.
So how do you produce these surfaces? Which methods you are using?
Sure. Yeah, let's consider, let me take one of the visual. Okay, let me use this visual. So you see there's a device. If you want to make SLM, it's more complicated. But for this, there are a few methods. So I first used the lithography. I just made an optical system which images the light distribution on the substrate and then selectively etching the material. Is this a good method? Not perfect, but it's okay. That's the first thing I did. The second thing is we bought a direct laser writing machine. So this is this creates local intensities. It writes step by step. So there are devices making those structures. For example, Heidelberg in Germany makes these devices. And if you have $500,000, you can buy one and enjoy it. Or if you have a couple $1 million, you can buy electron beam lithography machine, which is the best machine ever. The E-beam lithography, I'm sure maybe most of you are familiar with. It's used for semiconductor fabrication as well, but it's pretty nice and very sensitive, but very expensive and slow. So basically, I summarize 3 methods: simple, inexpensive, lithographic. You can make in your lab. Pay some money and get a laser writing machine from anywhere. Maybe Heidelberg is the best, and buy a E-beam machine. Maybe I don't know what Middle East Technical University have. Maybe they have those machines. I'm not sure. Most universities have it. Some universities, and if your university have it, you can create your own. I think it's really fun to work on this stuff. And if you're in university, you should enjoy, because if you go industry, everything is expensive. But if you're a student, you can use the university's resources as much as possible.
So these surfaces are photoresist, am I right?
Okay, no, not this. Not this surface. This surface is transparent. Let's say glass.
Glass.
Okay.
Yeah.
Let's say glass. Yeah, glass. Just ordinary glass. But in my work, we use plastic. Plastic is much more easier. Easier to fabricate and use. But for high power applications, you don't want to use plastic. You want to go with glass. Maybe in one application, I couldn't proceed because it was really high power. So I ended up, I need a diamond. An entire surface should be diamond. So it's pretty expensive, actually. You don't want to make it. It's a diamond ring, not a diamond ring. It's a diamond holographic element. It's quite expensive. But yeah, I would say there are companies fabricating for you, and you can just tell them what you want. If you want glass or plastic, that's okay, and they can put anti-reflection coatings for you if you want as well. Anti-reflection coatings can be applied. Yeah.
Another question: is there any progressing work? The wavelength, actually, the wavelength is important for me. You mentioned always the visible wavelengths. What about the infrared ranges? Is there any work going on the infrared ranges?
Yeah, definitely. The industrial, okay, so one of the thing of industrial work is they generally keep it for them. So they're either they either get patents and they don't publish, or they just keep it as trade secret. However, the infrared is very similar to visible, right? So you only change the infrared. And another good news is as the wavelength increase, life gets easier. It's a rule of thumb. It doesn't work all the time, but if you work in infrared, okay, there are things change. So first of all, if you work in infrared, you should be careful because glass may not work for you anymore. You know, glass is good for visible, but maybe not for infrared. So you need to find material which is transparent for your application. And also you should consider the anti-reflection coatings based on your needs. But you can just sit down and design based on the wavelength you desire. That's, you know, after this, it's kind of straightforward.
Thank you.
Mm-hmm.
Thank you, Hocam. I was going to ask something about infrared, but there are two questions in the chat and they're similar. Let me proceed with
Please go ahead. Yes, go ahead.
Okay. What kind of software do you use for this kind of application? So it's CGI about design.
Yeah.
And let me ask the other one because it's similar. He asks, do you use like ZMax kind of optical design softwares?
Yes, for this kind of things, I definitely don't suggest ZMax. Okay, let me go here. So I define three main areas, right, for advanced light shaping. For this kind of things, definitely ZMax. It's kind of standard tool, but for the CGAs, I always use MATLAB for this because you can manipulate bit by bit. You create a CGH matrix, and everything else is straightforward. Yeah, for this I always use MATLAB, and I suggest MATLAB to use.
Thank you, John. If we go back to infrared, I was going to ask when we apply processing on silica, we have many problems with infrared wavelength because it burns, it damages the silica. And I was going to ask if plastic works with not infrared, but your wavelengths, or which kind of plastics do you use? I mean,
I see. Yeah, so I will suggest you. Okay, I will suggest you a general method for this. First of all, find the name of the plastic. The most common two plastics in industry are those polyethylene and polycarbonate. Okay, so again, polyethylene and polycarbonate are abundant and very, very inexpensive. So these two plastics are what you need maybe. So for this, for specific applications, you can just go to Google. You know, God bless Google because you can find everything now, and just go find the specs of these materials. You know, how much absorptance it has, because if your material cannot resist, it means that it absorbs and creates heat. So you can just make your own calculation by using the specification sheet. And then if it fits to you, you can just find which company is making this for me, or I can make it for me from this lab or things like that. So it's a step-by-step process, but everything else you can, everything you can find yourself as long as you know the methodology and the main point.
Hocam, actually we kind of use the infrared for diffractive optical elements in our department, like a few professors working with them. So I was always wondering if it damages, how do we create such structures with infrared? But thank you.
I mean, how much power we are talking about here? How much power?
I think we have femtosecond and we have like hundreds of milliwatts.
I see. Yeah, femtosecond laser. Yeah, that definitely. Yeah, for this, okay. I don't know. Okay. I'm not sure. You need to, as I said, you need to investigate by looking at the sheets. But for now, I can say plastic is not good for you. Okay, plastic is not good for you because plastic, we know it depends on the wavelength first. You know, depends on everything, a lot of parameters. But for now, I can say I wouldn't put my money on plastic. I don't think it can resist. But glass, I don't know the which wavelength we're looking for, but look at glass. Glass can be good for you, I think. But just a guess, just make your calculation.
Thank you, Hocam. There's another question in the chat.
Can I ask a question before this?
Of course, type.
Yeah. Okay.
You passed quickly through the eigenvalues thing of calculation for the systems, the optical system that you were doing. Was it about calculation of the design of the system itself or more about shaping?
Yes, the eigenvalue, okay. The eigenvalue equation is not about calculating the CGA. It is the equation, I mean, the governing equation of the laser cavity. So consider the cavity, okay? So whatever repeats itself can be defined by an eigenvalue equation. That's why it's useful in, defining the wave structure. So in this case, whatever repeats itself is called mode, right? A laser mode is whatever repeats itself for each iteration. So that's why it's suitable for the eigenvalue equation. And if you look at this equation carefully, you see the eigenfunctions and eigenvalues. The eigenfunctions are the modes, the relative modes. For example, this one, the eigenfunctions are the TM00 and TM01. Okay, and the eigenvalues, the corresponding eigenvalues are the corresponding power. How much dominant it is. How much dominant? For example, if this one, maybe I would say half, like half is TM00 dominant, half is 01 dominant, things like that. So basically, this is to define the cavity itself. It's independent of the CGH.
Thank you. Okay, there were a question in the discussion. It's about our lab product.
Yeah, I saw it. Let me answer that. Yeah, so there's a company called Rpc Photonics, right? Maybe probably you haven't heard that. So Thor Labs made an agreement with them, and Rpc Photonics, it's a New York-based company, are fabricating those structures for them. And that's right. For example, this is kind of an engineered diffuser, not exactly the same. It's a little bit different, but yeah, you can definitely. This is a diffuser. Okay, this is a diffuser, and that's very similar to what they sell.
Thank you so much, Hocam. Are there any other questions?
We usually use.
Okay, I'm sorry.
We usually use the Fourier transform to calculate the shape or how much the radius of diffraction limit, or get some information about the image constructed at the image plane. But here you said like the Fourier transform, we can go upon it to similarly shape something at the image plane. Is that correct? This is what?
Yeah, okay. So there are two different worlds we're talking about: design and operation. Design is here, operation here. So let's go to the design. Okay, let's go to the design. Design is here for this. Okay, so you take forward transform, Fourier transform, and backward Fourier transform to design the structure. It's a well-known algorithm for the designs. So when you finish designing, you go to the lab and you want to see what's going on. And then here, you take the Fourier transform to see what's going on, okay? So but this is for the far field. For the far field. But okay, you can also ask, if I remove the lens and if the distance is small, what's going to be? Or you can say that, oh, I put the screen not on the focal length. What am I going to see? Okay, if you ask this, you should definitely go to the equations, go back to the Fourier optics. Okay, and you calculate these then. You calculate those. So basically, you just propagate the beam. You can calculate anything you want as long as you know how the electromagnetic field propagates in space, right? So you pass the Fourier domain, propagate them back to spatial domain, and that's it. I strongly suggest you guys to learn those if you want to be serious in optics and learn how to use MATLAB or Python. Python is also useful for you to, you know, for those simulations. Yeah, that's what I can say.
May I ask a question?
Yeah, sure.
This might be a ridiculous question because I don't know that much about optics. I'm a freshman student right now. Actually, I have two questions. The first one is, to what extent do these images visible? Like you gave an example about traffic lights. In some traffic lights, there are some people moving. Like with these technologies in these days, can we choose that image, or can we just see green lights, or can we select the moving person on that traffic light?
I see. Yeah, that, you know, most of the optics, for example, we won't see because they're in infrared domain, like LiDARs, like cell phone, you know, the cell phone recognition systems. They're mostly in IR, so we don't see them. But yeah, for traffic light, yeah, my example was a stoplight for cars. For traffic light, I don't know. You can come up with something innovative maybe. But currently, I think people are happy with the traffic lights. You know, they just live with it. That's, you know. But since, you know, there are some domain, like human eye can see some range, you know, 400 nanometer to 700 nanometer. So this won't change. So you know that this won't change. So this visible region will stay the same as no matter how the technology will develop. So there will always be some emphasis on the visible range. However, infrared is also very important in defense, in IT, or anywhere. I would say, you know, visible infrared. UV is maybe not too much, but there are also cases that UV also important. Yeah.
Okay, thank you. So I have the funny question actually. In the future, will there be a communication style like in Star Wars, like holograms will stand up and will talk with us? Is there a possibility like that?
Well, let me correct your question. There, it still exists. I mean, it's here. That
Is it exist?
Yeah. You need to see if you go to, as I said, the Optics and Photonics AR VR meeting by SPIE. You guys probably know that, right? It's held in San Francisco. I mean, there are a few SPIE conferences. One in San Diego. This is also nice, but they don't show. They don't have a display room there. But if you come to San Francisco, but I'll tell you even more interesting. Okay, this, you know, the Star Wars Obi-Wan Kenobi is not very interesting anymore. It's there. Okay, I'll tell you that. I've seen the Iron Man thing. You know, there's a goggle. You see everything 3D here, and you can touch things, and things change. Like, you know, you can do that. Amazing, you know, amazing things you can see. But you know, in industry, it's not very commercially profitable. For now, you can buy some virtual reality from Facebook. They're selling this. But I'm not sure if, you know, how bright will the future about this AR VR thing. You know, it's kind of a luxury kind of product.
Are those
yeah,
products cheap enough for us to buy, or are they like?
Yeah, you can. I don't know how much. Like the Facebook thing, I don't know how much I don't know the. Also, Microsoft has it. You know, HoloLens is there for you if you want to buy. I don't know the capabilities, but they're kind of surprising. But you know what? If you buy it, you will enjoy in the first week, maybe second week, but not third week. That's the thing. For now, it's not like compute. It's not like a mainstream thing. So, but you know, there are other things like, you know, people always think visually. Okay, visual things are cute, but you know, for example, the cell phone recognition system, you don't see anything, but it's very useful. Very useful things there, but you don't see anything. So in terms of functionality, it can be a little bit different. You know, it's not like hocus pocus, but it's very, very profitable. You know what I mean? Yeah.
Yeah. Oh, thank you then. By the way, I searched the HoloLens and they are $3,000.
How much?
$3,000.
Ah, okay. Yeah, start saving. Start saving. Yeah, yeah.
Thank you for your answers.
No problem.
I remember that when Obama won the election, there were 3D news reports. They were using like 30 cameras to film it, and it was 3D. That was the first in-life use of 3D I heard, but I think the technology you mentioned about hasn't reached Turkey yet. Or if it
there are lots of methods making that. You know, they took lots of cameras, but is it effective? Because this technology was old. You know, using lots of cameras, or you can go to the cinema for 3D imaging. This is cool, but not very new techniques. There are a lot of new techniques, different techniques, which even I don't aware of. I'm not aware of most of it, but different techniques that they are using for this. But commercially profitable ones are, as I mentioned, the goggles. The goggles are mostly using the HOEs. I tried to mention the holographic elements for reflecting lights, see-through displays. There are other similar technologies, but this is a brief summary.
Thank you, Hocam. But do you think in time, Fırat Hocam, I think you were going to say something.
In fact, I would like to comment, Alkan Hocam, especially for this see-through goggles and AR/VR lenses, this kind of end-user products, they are becoming very popular in industry, because after this COVID, with the restriction of travel, mainly with this industry 4.0 and later, people are trying to transform their maintenance and repair teams to be working with their AR/VR goggles. So the operator wears the goggles, and the main supervisor, seeing through the lens, tells them what to do, and by holographic imaging they can see what are the parts they have to change, and also training of the machine parts, repair parts. These are some important aspects of this technology, I think, and they are becoming very popular.
Yeah, research is going on for this. I mean, academic research is going on. Industrial research also keeps going. This is one of the hot topics in optics. You're right. Yeah, it's getting more importance as we humanity face with different problems like COVID or other things, you know. But you know, image quality is still an issue. Yeah, image quality is still an issue, and a lot of areas to develop.
Thank you, Hocam. This technology is still not much familiar for us, but I think industry is a few steps away from us.
Yeah, I just tried to talk about some, flashing points, but this is a very broad area, optics. Currently I'm designing intraocular lenses, and it's a pretty cool area. It's very profitable, actually. So you cannot definitely, it's not a 3D image kind of thing, but it's really nice to design those things and make people see brighter. But optics is, you know, always open to development. I think it never ends. It keeps growing.
Actually, this was one of the questions we wanted to ask during the panel. The photonics is kind of having its like 16 feet, I'm sorry, 60 years, if there's such thing. So it's been a long time since the first creation of laser. And now quantum technologies are like more popular. People are focused on quantum. So do you think photonics will live a longer life, I mean, in the future?
Yeah, so consider, okay, just one example. When I finished the Middle East Technical University, there wasn't, actually there was maybe one or two optics departments. Now there are a lot of optics departments are growing in US and maybe other parts of the world. New fields appearing, new research areas, and now optics is just mainly a field. Photonics is as well. Maybe I think there is also one in Turkey as well. Maybe a few optics departments similar. So I would say, yeah, I would expect a even larger growth for the future decade. And yeah, it's definitely a nice area to grow in.
Thank you, Hocam. Actually, we can direct this question to Fırat Hoca and Alpan Hoca. Maybe they have some things to say about the future of photonics. Okay, let me repeat the question. So quantum technologies are more popular nowadays. Do you believe that photonics has a broader future, like from now on?
Well, of course. I mean, if I didn't believe that, I would be still, you know, doing my research and continuing to develop new projects in the field of photonics. So it's always evolving, always developing. There's no end to, I don't see an immediate end to photonics research. I mean, actually, it's one of those fields which still bears quite a lot of potential for new stuff. It will not stop with the quantum technologies, quantum information, quantum optics. It will go on. So, yeah, because you know, we're exploring more and more materials, and as we explore materials, their optical properties emerge to have unexpected functionalities and potential applications. So it's like a bilateral kind of research. So the more you do research with light, you explore more materials. The more you explore materials gives you more capability to do research with light. So it's both two ways. So will the materials research end soon? No, I don't expect that. Neither will the photonics research end soon. So my short answer.
Thank you, Hocam. What you mentioned is, I think, quantum optics, is it? I mean, I don't know much about
quantum information technologies rely on, of course, quantum optics, quantum optical optical interactions at the quantum limit. Let's put it that way, maybe for you. So there's a lot of research going on in coding or encoding information into quantum mechanical bits. So information bits, ones and zeros, into quantum mechanical states. And these quantum mechanical states are classically speaking, first established experimentally using superconductors. However, more recent than that are those quantum bits which are produced, or let's say stored in by optical means in quantum mechanical interactions in materials in the form of electromagnetic radiation, and mostly in the visible or near infrared regime. This is where we are in the domain of quantum optics. So you treat light as a quantum mechanical entity, just like an electron in a box, in a potential well. You can do the same for photons in a corresponding potential well. Okay, and the simplest put quantum optics. However, there is more to that, of course. It's a lot, it has a lot of detail, but it's it has been entertaining quite a lot of interest in the last 15 years or maybe 20 years or so, quantum optics. Previously, it was all theoretical, but it became quite experimental. And nowadays, people are working mostly on interfacing between superconducting quantum bits and optical quantum bits, because you can do quite nice processing of quantum information using superconducting quantum bits, but you cannot transport it. You can do transport with optical quantum bits. So now one needs to engage the information, quantum information, in the processing part and the transport part together. Therefore, one needs to, we need to develop schemes which are at the interface of superconducting quantum bits and optical quantum bits together. And it's not that easy, because these are two completely different kind of domains, and one needs really very clever solutions, including optomechanics, electro-optical modulators, acousto-optical modulators, etc. These secondary, tertiary optical effects are used to couple into superconductive quantum and vice versa. So there is quite a lot of research right now in that interfacing.
Thank you, Hocam. So you say with these hybrid areas, photonics will live long, so we can keep our research on the photonics. I mean, as students, because it's kind of our future.
Yeah, of course. Well, I recommend you to be aware of recent developments in this field. Don't distance yourself from the most recent developments. Try to follow, if not very professional journals, but at least popular journals, scientific journals, to keep yourself up to date with the most recent developments, because these popular science journals give quite a lot of space to interesting potential applications in quantum information right now.
Thank you, Hocam. Is there anything you would like to add? Okay, is there any question about in general? Okay, then. In Turkey, it's almost 10 p.m. and in US, I think it's the day like just starting. So thank you for all our participants. Thank you, Alkan Hocam, Fırat Hocam, Alpan Hocam, for your speeches and presentations. We are so happy to have you today. And so good evening for those who live in Turkey, and have a nice day for you.
Pleasure is ours.
Thank you very much. Thank you very much. Great event. Thank you.
Thank you very much.
Thank you, Hocam. then see you on the following events, hopefully.
Good morning.